For determining the length of the track, we first started with a calibration curve for the power being sent to each motor and the speed at which the car runs at that power. So we did this by creating a calibration curve by having the car run straight for 10 seconds, and then we measured how far the car went during that 10 seconds. We did this for 7 trials and we averaged the results out. And then we also did a similar thing for when the car is turning. For turning, we also had it set to run for a certain amount of time, and we determined how far the car drove during that time, and we averaged out the results from multiple trials for both turning left and for turning right. The code keeps track of how long it spends in each of the if loops being going straight, turning right, and turning left. By keeping track of how long it spends in each one, we can multiply that by the speed that it goes during each of those if loops. And by multiplying the time in the if loop by the speed, we can get our distance for each if loop, and then we can add them all up to determine our total distance around the track.
A few of the lessons we learned that motors don't work with servo commands. When we had 2 separate codes, one where the motors would follow the line well, and then another where the servo would move. When we tried to combine them, it didn't work. We had the servo library in the motor code, and that worked, but then when we tried to actually add servo commands to the servo to make it move, it wouldn't work. So it doesn't seem that you can do that. We also learned about the LCD screen. When we first started using it, we kept on getting these weird symbols, and what we figured out is we had some of the pins wrong, and we finally got it to display the total distance, and from that calibration curve find the number. We also learned how to use the photoresistors. We learned that ambient light really does affect the photoresistors, so that's why we had that covered. We also learned that the LED, the white had low emittance, and the black had high emittance, even though it seems like it would be otherwise. Improvements. If we were to improve the vehicle, I think one of the first things we'd do is add front wheels, because the sleds on the front of the vehicle would get stopped sometimes. We could also put the wheels in the front of the vehicle, but we'd have to change the configuration of where the photoresistors are.
And then for an improvement would be for our distance calculator. Instead of having a calibration curve, which may be a bit inaccurate, we can use a photoresistor inside the wheel to determine how many times the spoke of the wheel crosses the path of the photoresistor, which will change the value that the resistor is getting. And then from that, we can determine our angular distance, which we could easily convert using the circumference of the wheel into our linear distance, which would be a much more accurate measurement than having it be determined using the if statements and motor speeds, which may vary slightly.
Another thing we'd like to improve is a better line finding algorithm. So right now we kind of have it set as a hard code of when the car will approach a line perpendicular. So when it approaches the line perpendicular, it'll be able to then turn left and a certain distance, and then it'll be able to catch the line using a line following algorithm and then be able to follow the line after that. But what we would like is to be able to get the code to approach the line from any direction at any angle and be able to turn itself accordingly based on the readings it's getting. So for instance, if it approaches on a curve, it'll be able to turn left or right a certain amount so that it'll be able to catch itself onto the track, meaning that in between both sets of the photoresistors and LEDs, that the black line will be in between both of them.
This concludes our presentation. Thank you.